If I ask you to group change my password with forgot my login, you don't even think about it. Your brain makes the connection instantly. And if I throw in a third phrase, like what is the weather today, you immediately spot the odd one out. You inherently understand human meaning. But historically, computers haven't worked that way. Traditional databases don't comprehend ideas. They are rigid systems that simply scan for exact character matches. Take the words puppy and dog. A human knows these are closely related, but look at the spelling. There is 0 letter overlap. To a traditional search system looking for exact characters, these two concepts have absolutely nothing in common. This rigid logic is a massive roadblock for generative AI. AI models don't have biological brains to intuit concepts. They only process math. To make these systems actually useful, engineers had to find a way to translate the qualitative, abstract human concept of meaning into hard, quantitative data. You might have heard of tokenization, but that is really just chopping words into smaller pieces so a machine can digest them. Parsing text is not the same as understanding it. To capture the underlying relationship between pieces of information, the system uses vector embeddings. Here is how an embedding LUNL works. It takes a word, like cat, and converts it into a long list of decimal numbers. To humans, this array is illegible gibberish, but to an AI, these numbers act as precise mathematical coordinates. By turning words into coordinates, we force language out of the realm of linguistics and into the realm of spatial geometry. Imagine a massive mathematical map. Every array of numbers is plotted as a physical point in this high-dimensional space. Because the coordinates are derived from meaning, related concepts like puppy and pet are assigned specific numbers that force them to cluster tightly around dog. Introduce entirely different ideas, like car, road, and vehicle, and their coordinates group them in a distant sector of the map. An unrelated word like pizza gets assigned unique coordinates that push it to the far, isolated edges. This establishes the absolute governing rule of this mathematical universe. The shorter the physical distance between 2 points, the more identical their meaning. And this mapping process is not restricted to single words. You can compress entire sentences, paragraphs, or even images into single plotted coordinates. This allows embeddings to take paragraphs, images, and complex corporate documents and map all of them into a single navigable coordinate system. In the enterprise world, this solves a critical problem. A company cannot cost-effectively feed its entire library of HR policies and manuals to an AI every time an employee asks a single question. Instead, companies use a vector database to convert documents into vector coordinates. When an employee asks a question, the system translates it into a new glowing coordinate point. A search radius expands, extracting only the physically closest document dots. The system then takes this highly relevant, localized cluster of data and feeds just that small package to the generative AI to formulate a precise answer. This exact workflow is called Retrieval-Augmented Generation, or RAG. It is the architecture that makes AI practical, fast, and domain-specific for modern businesses. But there is a primary flaw to this technology. Vector systems calculate proximity. They calculate similarity. They do not calculate objective truth. If the underlying database contains bad information, or if the documents are poorly chopped up, the AI will confidently retrieve data from the wrong spatial cluster. This is exactly why clean data and careful human review remain absolutely essential, especially when applying embeddings to high-stakes fields like law and healthcare. When an AI identifies the correct answer within a vast archive, it navigates this multi-dimensional map, moving directly to the coordinates of the requested meaning.